This is the origin of the cosmic microwave background that we see today. Let's let this volume of blue dots represent all of space at that era. Then let's focus our attention on this tiny portion that has a radius of about 42 million light years. This is the region that will be all of our observable universe in 13.7 billion years. Our Earth will form somewhere in the center of this region in about 9 billion years. But we have a lot of expansion to experience first. Imagine that you are standing on a 100-meter track and someone 99 meters away is going to walk toward you. There's the starter's pistol, and the walk begins. But there's a problem. The track is stretching, growing longer as he walks. He takes a 1-meter step every second, but the track grows 1 meter for every 100 meters every second. After 10 seconds, the walker has taken 10 steps, but the remaining 89 meters has grown so that he still has 98 meters from you. Another 10 seconds, and he's still almost 97 meters away. It will take him 460 seconds, but he will eventually reach you. And during that time, the track is stretched so that it is now 10,000 meters long. The other end of the track is now moving away from you much faster than the walker can walk. If he had to start there now, he would never get here. And the question of how far he walked is ambiguous. We could say he walked 99 meters because that was the distance at the beginning, or we could say that he walked 9,900 meters because that was the distance at the end, or we could say 460 meters because that is his normal speed times the time it took. The expanding universe exhibits the same characteristics. Light from the edges of the 42 million light-year sphere began their journey to the spot where the Earth will develop about 13.7 billion years ago. But during the trip, the intervening space multiplied itself 1,090 times. And now the spherical shell from which the light began is about 46 billion light years away. This is the farthest into space we can see right now, and it is called our particle horizon. 100 million years after inflation, the first stars formed. They were massive giants that formed in every region of space, including our little sphere of observable universe. Those that formed on a shell a little inside our expanding particle horizon are just visible today. The light from these primitive giants has been traveling over 13 billion years. And the shell of space where they formed is now over 36 billion light years away. So light from the microwave background was emitted from a distance of just 41 million light years away. And that distance is now 46 billion light years. And light from the earliest stars was emitted from a distance of 1.5 billion light years. And that has grown to 36 billion light years. Due to the faster-than-light expansion of space in those early years, the light was actually moving away from us for billions of years before the slowing expansion allowed it to start moving towards us. Light we see today from some distant galaxies that was emitted from 5 to 6 billion light years away comes from objects that were the most distant at the time the light was emitted. Massive objects like the Earth and the Sun, that are gravitationally bound to one another, can overcome the expansion of space between them. Space is expanding in our system, but the distance from the Earth to the Sun does not change because of this expansion. Why? Because as space expands, the Earth's orbit continually adjusts to keep the Earth at the correct distance that is demanded by the law of gravity. This is also true for stars inside a galaxy that are gravitationally bound, and is true even for local clusters of galaxies. As space expands, the distance between the bodies constantly adjusts to comply with the laws of gravity. The wavelength of light from distant objects is shifted toward the red end of the spectrum if they were moving away from us. And the expansion of space is measurable by measuring the redshift. And unlike the Doppler redshift, the cosmological redshift says nothing about the recessional velocity of the emitting object either at the time the light was emitted or at the time the light was received. Hubble's law says the further away an object is, the faster it is receding without limit. So, there are always objects far enough away to be receding faster than the speed of light. Objects we see with a redshift of about 1.46 are moving away from us at the speed of light, and all objects with larger redshifts are receding faster than the speed of light. Most objects in the extended universe are traveling away from us with velocities fast enough that we will never see them. In effect, we have an event horizon, and events beyond our event horizon are effectively unknowable to us. Objects that have a current redshift of about 1.8 are currently about 18 billion light-years away, and are now crossing our event horizon, never to be heard from again. Finally, this is a time sequence of the evolution of our universe. Big Bang, followed by inflation, reheating or the birth of matter, birth and death of the first stars, and the ongoing formation and growth of galaxies. When we look out into the universe, we are looking backwards in time, looking at the universe as it was when it was a lot smaller and a lot younger.